Hello, my name is Catherine, and I'm with Rafael and Nixon. And today we're going to be explaining our CPU scheduling simulator, which was built using Python with Tkinter for the GUI and Matplotlib for the visualizations. So we're going to start by running the program, and we'll add 4 processes using the input fields on the left panel. In P1, we're going to set arrival to 0, burst to 8, and priority to 2. In P2, we're going to set arrival to 1, burst to 4, and priority to 1. P3, we're going to set arrival to 2, burst to 9, and priority to 3. And in P4, we're going to set arrival to 3, burst to 5, and priority to 2. Each process appears in the process queue table as it's added, and you can also remove any entry by using the Remove Selected button. The algorithm selector on the left lets you choose from 5 algorithms: first come, first serve, shortest job first, priority scheduling, shortest remaining time first, and round robin. For round robin, an additional quantum input field activates when selected. We'll select first come, first serve and run the simulation. The results table populates immediately with each process's start time, finish time, waiting time, and turnaround time. On the right, 2 tabs update. The Gantt chart tab shows a visual timeline of process execution, where each colored block represents a process occupying the CPU. For first come, first serve, you can clearly see the convoy effect. P1's large block on the start holds up every process behind it. The statistics tab shows a bar chart comparing waiting and turnaround time per process, making it easy to spot which processes are suffering the most under a given algorithm.
Now let's move on to the algorithm comparison tab. What this one does is automatically run all 5 scheduling algorithms on the exact same set of processes and compare their performance side by side. So instead of switching algorithms one by one, we can see everything at a glance. So now we'll see at the left chart the average waiting time. So we will start with the average waiting time for FCFS, which comes at 8.75, SJF at 7.75, round robin is the highest at 12.75, priority scheduling at 7.75, and SRTF is the lowest at 6.50. Now we'll move over into the average turnaround time, the chart on the right. So we'll begin with FCFS at 15.25, SJF at 14.25, round robin again at the highest at 19.25, priority at 14.25, and SRTF at the lowest with 13.00. So as you can see here, for SRTF on both charts, it seems to be the lowest. So SRTF clearly wins on both metrics. The reason is that SRTF is preemptive. Every time a new process arrives, it checks whether the new process has a shorter remaining burst time than whatever is currently running. If it does, it will immediately kick out the current process and run the shorter one instead. This keeps the CPU constantly working on whatever finishes the fastest, which naturally brings down both waiting time and the turnaround time. So now we'll go to SJF and priority bars on each of the charts, on both charts, which both seems to be at the same exact height. So both at 7.75 waiting time and 14.25 turnaround time. This is not a bug, it happens because in our process set, P2 has both the shortest burst time and the highest priority. So when both algorithms pick who runs next, they end up choosing the exact same process in the exact same order, which gives identical results. In this case, it's exactly the same for both the average waiting time and the average turnaround time. Now we'll discuss FCFS, which comes in third. The issue with FCFS is the convoy effect. So P1 arrives first with a burst time of 8, so it runs completely before anyone else gets a turn. P2, P3, and P4 all have to wait behind it, even though some of them are much shorter. That unnecessary waiting pushes the average way up. Let's move to round robin on both charts here. Round robin has the highest numbers, 12.75 for the waiting time and 19.25 for the turnaround time. That's because with a quantum of 2, every process gets interrupted every 2 time units and sent to the back of the queue. All that switching adds up, but it's important to say that round robin isn't a bad algorithm. In real operating systems, especially time-sharing systems where responsiveness matters, round robin is actually the preferred choice because every process gets a fair share of the CPU and no single process can monopolize it. So, looking at both charts again, the takeaway here is that that there's no single best algorithm for every situation. SRTF minimizes waiting and turnaround time, but it requires knowing burst times in advance and has preemption overhead. Round robin is fair, but slower on average. The right choice always depends on what your system is actually optimizing for: throughput, fairness, or responsiveness. So now I'll hand it over to to the next person to walk through our AI usage.
For this project, we use DeepSeek as our AI assistant. We use it for three specific parts of the code base. First, the round-robin queue ordering logic. We kept getting incorrect waiting times when handling processes that arrive mid-slice, so we use AI to help generate and explain the correct approach. Second, the SRTF tick-by-tick simulation, which required tracking remaining burst times, detecting preemptions, and building the timeline all at once. Too many moving parts to manage without assistance. Third, the matplotlib Gantt chart drawing and segment merging logic, which wasn't covered in our coursework at all. The parts we wrote ourselves were the process class, the first come first served algorithm, and the compute averages function, since those map directly to what we learned in lectures. One thing we learned from this experience is that AI is most useful when you already understand the concept but need help with implementation. For sections we had no prior context on, we had to ask follow-up questions before generated code usually made sense to us. The most valuable outcome of this project wasn't just a working simulator, it was building a real understanding of why each algorithm behaves differently and what the trade-offs look like in practice. Thanks for watching.